scenario that we have, and then we're going to choose the type of neural network. Okay, so now remembering that all the neural network that we're going to use, we're going to parameters and hop on what parameters are. So before we start, any questions on what we did yesterday? Any questions? All right. So remember yesterday when we were showing how in the convolutional calculation, what will happen in CNN neural network. Okay, we mentioned that we have a kernel or a filter which will be applied to the input layer to get the feature map. So this is what I explained yesterday, where this is kind of a visual representation of that. So basically you have the feature map will be created by that, right? So basically we have this all filter which apply at each section of this image to create the feature map. Okay, so this is exactly what I was explaining yesterday. So yesterday we completed what you call this. We completed CNN. Any question on CNN, guys? Any question? Any CNN? Before we could move to what you call this? Before we could move. Sorry, guys. Can you see my screen? Can you guys see the slide? Can you guys see the slide? Can anybody confirm if you guys can see the slide?
Yes, we can see your slide.
Okay, it was showing inactive. Yeah, as if I'm sharing a different screen. All right, so guys, does anyone, do you guys remember the component, the structure of a CNN? What do we have in a CNN? What do you remember that we have in the CNN? What do you remember in a CNN? What type of layers do we have?
For neural network.
Yeah. What do you remember that we have in a CNN?
We have a convolutional layer.
Yes, we have a convolutional layer. What else do we have?
A pooling area, pooling layer.
Okay, pooling layer and
a fully connected layer.
Yes, perfect. So that is very important to note. And another important thing to note is in what type of scenario do we need to use a CNN, a convolutional neural network?
When dealing with images.
Perfect, perfect. So those are the most important things that you need to note about CNN. So I'm just going to show you a short clip, which will basically guys, just give me a second. I'm trying to share this, but this team is just freezing. Yeah, sorry guys, I was just restarting this team because it was giving me problems. I'm just going to share this. We're just going to go through this short clip here. I hope you guys can hear me. Can you guys hear me?
Yes, we can.
All right, thank you. All right, so
and how the structure of the artificial neural network was conceived, to working through an intuitive example covering the main aspects and some of the many complexities of deep learning. Now, all these videos have only been focused on one type of neural network, the feed-forward network. The focus of this video then will be to initiate discussion on another very popular and important neural network architecture, the convolutional neural network. For our discussions on convolutional neural networks, we will go with a very common example, number recognition. The reason this example was chosen is because of this great interactive resource by Adam Harley, a robotics PhD at Carnegie Mellon University. I have linked the resource in the description so that you too can experiment with it and see the internals of a convolutional network. Now, if you can recall from our example on an image pattern recognizer using a feed-forward network, we set up an idealized system and made the assumption that each hidden layer in our network would build upon further layers of abstraction, from vertical lines to combinations of vertical lines. However, in actuality, as we explained, this wouldn't happen, and the receptive fields in the network would be a lot more random to the human eye due to the architecture of feed-forward networks and how they compute. With convolutional networks, however, this isn't the case, and we could to some extent see these layers of abstraction building up. Before we delve into why and how this happens, let's first set up a structure for the network we will be using. As with our previous example in image recognition, the input will be the individual pixels of our image, and the output the patterns we are trying to classify. In this example's case, we have 10 outputs, numbers 0 to 9. For the layers in between, we will have 2 convolutional layers, 2 pooling layers, and 2 fully connected layers. Now that was a lot of new terminology thrown around, so let's break it down layer by layer, starting with the input. While we have already stated that the input is the individual pixels of the image, I want to mention some important details about how a computer views this image. Every image in a digital device is stored as a matrix of pixel values. This is referred to as a channel, a certain component of an image. Now with a typical digital camera, every image will have 3 channels, red, green, and blue, RGB, which you can imagine as 3 2D matrices stacked upon one another. For the sake of simplicity, we will assume our input has just one channel, the luminance of the image, with the value of each pixel represented in 8 bits. In other words, the pixel values will range from 0 to 255, with 0 indicating dark or transparent luminance, and 255 is bright. As a side note, digital systems store all types of sensor data and other information in this fashion. For example, for a convolutional network that would operate on speech, we could represent that speech as a matrix of frequency values. Coming back on topic, now that we understand the format of the input, let's finally delve into where the real magic happens, the convolutional layer. As you can assume, this layer and the network as a whole get their names from the convolutional operator, which in layman terms is a mathematical combination, in other words, the dot product of 2 functions to produce a third function. In CNNs, this operation is implemented in what is referred to as a feature detector, filter, or most commonly, a kernel. You can think of a kernel as a mini matrix, orders of magnitude smaller than the input. In a convolution operation, then, the kernel moves across the input image, taking the dot product of the 2 matrices and then saving the values to a new matrix, dubbed the feature map of the original image. At this point, you may be wondering how this is able to detect any features at all. Well, if a kernel is initialized with the values in a specific configuration, they can be used to transform an input image and find various patterns. Take these kernels, for instance. When loaded with the appropriate values and convolved with the input image, produces an output which highlights various edges in the photo. Now, I won't delve into the specifics of the various types of kernels in this video, but there are many resources that talk about them extensively, such as Computer File and their various videos on kernels like the Sobel Edge Detector. Coming back on topic, as you can see, kernels are essentially ways to do fast computation and produce a new output. In this case, we're doing it with an image, with an effect or features highlighted. Programs like Photoshop use these simple kernels for effects like blurs, for instance. Now, when we look at a typical image, take in how much is actually going on. There are various edges, shapes, textures, etc. that stack together to make various objects and the overall image we are looking at. At the start of a convolutional network, the types of kernels we use would be quite simple and more geometric, detecting things such as edges, corners, and simple shapes and patterns, like a circle, for instance. Additionally, each convolutional layer can have multiple kernels that produce multiple feature maps of their own. So for our example, we can see that our first layer has 6 kernels, and these kernels are detecting simple patterns like horizontal lines, vertical lines, and corners on our drawn numbers. As a side note, for each of the convolved pixels in our feature map, a nonlinearity function was also applied, in this instance a ReLU. We discussed this function in previous videos and the need for nonlinearity in neural networks, so our feature maps are more adaptable to real-world data. Also, you can now see how complicated this process would become if we had more than one channel, as each channel would have 6 feature maps, in this instance leading to 18 for an RGB image, and then those feature maps would have to be filtered together or operated on separately depending on your specifications. For instance, in a self-driving system, a red hexagon is a stop sign, so we would need separate channels and kernels for those channels. However, coming back to our example, just one channel, luminance, was more than enough. Moving on, now that we have a rectified feature maps, the next layer in CNNs after the convolution is a pooling layer. Pooling layers are used to downsample our feature maps, keeping the most important parts and discarding the rest, and primarily done to reduce the overfitting rate and so that calculations can be sped up in later layers due to the reduced spatial size of the image. The type of pooling our network implements is max pooling, in which we take another kernel and slide it across our input feature maps, and the largest pixel value in that region is what is saved to our new output feature map. As you can see in this number classifier, the max pooled layer still retains the important information from the convolutional layer while being smaller in spatial size. For instance, in this feature map, you can still make out the horizontal lines, and in this one, the vertical, from their respective original feature maps. So now, with the defining layers of the convolutional neural network understood, A, the convolutional layer which extracts features, and then B, the pooling layer which downsamples the feature maps, the next step is repeating these layers to build up more abstraction in the network. As stated earlier, in later layers of the network, more complex kernels are incorporated that detect shapes, objects, and other complex structures, which is done by leveraging the previously generated feature maps and their detected simple features to build more complex ones. This is essentially the definition of abstraction. You can see in our example that in the next convolutional layer, there are 16 kernels, and these kernels are now much more complex. In the first convolutional layer, we were detecting simple edges and corners, and now, as you can see, horizontal and vertical edges are being combined, as well as other simple shapes from the previous feature maps. For instance, with this drawn 4, you can see this feature map combining both horizontal and vertical edges from various earlier layer feature maps, and resembling a bit of the structure of a 4, or with these feature maps of a 5, where diagonal lines and S-shaped patterns are being detected. As you can see, similar higher level features are present for all numbers. Now, after this convolutional layer, just as before, there is another max pooling layer to reduce the spatial dimensions of the feature maps before the fully connected layers. As seen here, with these newly pooled maps, they look a lot more random to the human eye, since the spatial resolution is not very low. However, to a computer, they are just the key points in a matrix that represent a drawn number. You can also see now why we needed these pooling layers. From a raw input 32 by 32 pixel image with 1024 pixels and no discernible features, to 6 low-level feature maps of size 14 by 14 pixels resulting in 1176 pixels, and then finally 16 high-level feature maps of 5 by 5 pixels resulting in 400 pixels. And this in general was the whole point of these convolutional and pooling layers, to detect high-level features with as low as possible spatial resolution, and why this part of the convolutional neural network is referred to as feature extraction. At this point, with the features extracted, we still need to be able to classify them, hence the second part of the convolutional network, the classifier. This part is comprised of fully connected layers, similar to a feed-forward network, except now our input to these perceptron layers are the high-level extracted features from our input, rather than the raw input pixels. In this example's case, there are 120 neurons in the first fully connected layer, and 100 in the second, and as you can see, these are sufficient to correctly classify numbers with a high degree of accuracy. Now, I hope you can recall, as we've covered in videos past, during the process of backpropagation and gradient descent, the weight and bias values are tuned as the network learns. In terms of convolutional networks, those values would still be altered during this process, and also other values, such as the kernel coefficients of our convolution and pooling layers. Now, before continuing, I want to stop and highlight the fact that in our discussion of convolutional networks, we have made many generalizations and overlooked many details. For instance, hyperparameters like kernel size, stride and dilation rate, transposed convolutions and padding, different types of pooling layers, as well as other parameters and hyperparameters in our feature extracting layers and their effects on the output. Not to mention the impact of all the parameters in our fully connected layers, which we already mentioned in previous videos. If you want more information on these topics, check out the sources in the disclaimer and description below, as they are beyond the scope of this video. Coming back on topic, throughout this video we've now seen how and why convolutional networks excel at tasks related to image classification. However, where they don't perform well is for tasks such as natural language processing. This is because these tasks require memory, but not to fret. There are networks designed specifically for this, that among others will be discussed in the next video in the series. However, this doesn't mean you have to wait to learn more. If you want to learn more about deep learning, and I mean really learn about the field, from how these artificial learning algorithms are inspired from the brain, to their foundational building blocks, the perceptron, scaling up to multi-layer networks, different types of networks such as convolutional networks and recurrent networks, and much more, then Brilliant.org is a place for you to go. For instance, in this section on convolutional neural networks and the artificial neural networks course goes through many of the concepts we have discussed in this video. Now, what we love about how the topics in these courses are presented is that first an intuitive explanation is given, and then you are taken through related problems. If you get a problem wrong, you can see an explanation for where you went wrong.
Right, guys. So this was an example of how RNN is actually used. I'm just trying to, how CNN is used. So basically, that's what those kernel are actually doing. So they're basically going through the pictures and creating a feature map of that picture. Remember, CNN is all about dealing with images, So with that being said, is there any question on what you've just watched? Maybe you have a question on that. You guys have a question? Any question? Any question?
Yes. It's not a
Alright.
question, but like the video, there was an echo on the video. Can you please share with us?
Sorry, what you saying?
There was an echo on the video. It was almost as if there were two people talking at the same time.
Oh, there's an echo. Guys, they've said it during the video. I understand it's because of because my sound was also on, so it was actually sending back. But basically, the video is all about it's kind of a visual representation of what we spoke about yesterday, how the convolutional neural network works. So the video was just about showing you how it can work with an actual picture, what it does with an actual picture. You see, I've mentioned many times that I've given you the example of a picture with 28 by 28 pixel, which means the input layer will be taken, and from the input layer, that's where the convolutional kernel will be applied, and which will create a featured map. All right. So just to make sure everyone understand, let's say you have a picture of 20 by 20 pixel. Those are the size of the picture. How many layers will you have in the input layer? How many layers do you have in the input layer if you have a picture of 20 by 20? How many layers will you have?
400.
Perfect. Is there anyone who doesn't understand where the 400 is coming from? Anyone who doesn't understand? You need to speak now or forever hold your peace. Anyone who doesn't understand? Anyone who doesn't understand where is the 400 coming from? Okay, then can anybody else tell us where is the 400 coming from? Anyone, you can unmute yourself and tell us where is the 400 coming from? Why she said 400?
Isn't it 20 multiplied by 20?
Yes, perfect. So if we have 20 pixel vertical, 20 pixel horizontal, the total is going to give us 400. So we have a total of 400 pixel, which will be used in our convolutional network. So, so what does that mean? Sorry, I think I'm not sharing the screen. Give me a second. Okay, so what does that mean? That means that this is an example of what we have. We have a picture of this bird here. So in the picture of this bird, depending on the size of this picture, in pixels, so if this picture is 5 by 5, it means that we're going to have a total of 25 node in the input layer, which will have detail about that small pixel there. All right, so this is an example of an image 5 by 5. So the first pixel here at the bottom is giving us a 0. What does the 0 mean? It just means it's just talk about the shading, the details about that image that we have. So it's basically, when you think about it, think about the shade of that space, which can go from 0 to 1. So depending on how we are doing what type of images we have. So now we have that, which is put in a convolutional kernel, and then it's going to create a featured map. And then from there, now we have a pooling layer, which will take each part of the featured map based on a filter as well, or a kernel. It's going to get the maximum pooling and then get a certain type of images. So all this was explained in the video where you have it on a real picture. Okay. Yeah. And the last layer will be the fully connected layer, where in the fully connected layer, where we're going to actually determine what that image really represents in terms of probabilities. Okay, so the next neural network that we started was the RNN, recurrent neural network. The recurrent neural network is a neural network that is used when you're dealing with sequential problem. Sequential problem, what does it mean? It means that the type of data that you have are not data that are time dependent. All right. So if I give you an example of you are using it in a scenario of videos consisting of images. So how do you know? Let's say you have a video of a dog chasing a cat. So will you know that the dog is chasing a cat if you only watch, if this time the dog chasing a cat, if the video is about 2 minutes? If the video is about 2 minutes, by you just observing what is happening at 1 minute 42 seconds, all you will see is a picture, but you're going to have details. You're not going to know that actually this dog was chasing the cat. But you need to see what happened at 1 minute 30 seconds, what happening at 1 minute 31 seconds, so you need to know what's happening in different sequences to see what's the meaning of the video. All right. So basically, whenever now we're dealing with data that has to do with sequential data, it has to do with us remembering what has happened. Right. So for us to really identify the information in the data we're trying to see, we need to see a certain time passing. So we need to see a certain sequence of data. So whenever you're dealing with sequential data, the best you use the recurrent neural network, because this neural network is built for this type of scenario. So whenever you have scenario related to sequences, such as videos consisting of images frames, audio consisting of clips, and sentences consisting of words. So when you dealing in natural language processing, an example I can give you is your ChatGPT. ChatGPT you can't just give a word, you need to give a sentence. And the sentence that you are giving there, it's going to create a certain meaning. And before it creates a meaning, it needs to look at previous word that you've used. For example, I'm going to say, if I use the word book, okay, we're just going to show you what is a recurrent neural network. Okay, now I'm going to ask you a question. All right, so this is the input I'm giving you, the word book. All right, so can anybody tell me what does it mean? I just need one person to tell me. What does it mean?
It has two meanings. It could be like a book, as in a physical book, or the action of booking, like booking an appointment.
Yeah. So if you get somewhere, it's a written book. Obviously, if why okay, give me choose one. Let's say you say it's a book like a normal a physical book, right? So I have a physical book, and then you will call it book, right? A book. But if I tell you I'm going to book for my flight, does it still mean that book that you have to read? No. But how do you know it doesn't? Because you've looked at the sequence of my sentence, what I said before. I am going to book for a flight. Whenever you're dealing with a scenario where you have sentences which consist of words, so the meaning of this word book will depend on what is before and after this word. It will determine the meaning of the word book. If I say I'm going to buy a book, you know it's a book that you read. But if I say I'm going to book for a flight, you know this book is not a word, but it's a verb, right? So when you have situations like this, you use the RNN, recurrent neural network. So you can't use CNN here. CNN is for image processing, for operation with images. So when you have operation with images, you use the CNN. But when you have sequential data, you have a scenario that has a sequence, you need to use RNN. Such as another example I can give you is you want to create a model that will be able to detect and to determine what's the weather tomorrow. Because for you to know what's the weather tomorrow, you will need to have data about what was the weather yesterday, the day before yesterday. So basically, you look at a certain trend of what's happening with the weather. So that is a sequential data. Another one can be to determine the stock price tomorrow, looking at what is happening in the stock market in the past few days. You can determine what will happen tomorrow. So those are also sequential data. All right. So is there any question on this? Do you understand what's the RNN, recurrent neural network? Do you understand? Any misunderstanding? Yeah. Any question? Okay. All right. Cool. Now I want to show you now what's happening, the problem, the issue that you have with recurrent neural network. Right. I will need I need a volunteer. Who can be the volunteer to do? It's not that you have a question. We just want to do an experiment. Let me see. Okay, it's fine. Is Junior, what is that? Junior Maya, are you in class?
Yes, I am.
All right. So we're gonna try this with Junior Maya. Okay. Junior, are you able to? Do you know every number between 0 and 9? Right.
Yes.
All right. So for anybody else who has a pen or something, you're going to write down apart from Junior, right? So Junior, I'm gonna give you numbers randomly, right?
Okay.
Yes. So I'm just gonna give you 7 numbers out of the 10 numbers, right?
Okay.
So the first one is 9, 3, 7, 4, 5, 7, 2, right? Okay, so my question is this. Did I say any number that you don't know, that you've never heard about?
No.
But you heard when I was saying all the numbers, right?
Yes.
Can you please tell me what was the numbers that I said?
It's 9, 3, 5, 7, 2. I forgot the last one.
All right. So, guys, can you see what's happening? What's happening is that I gave him a sequence. The numbers were 9, 3, 7, 4, 5, 7, 2. But he remembered 9, he remembered 3, but by the time we got to 7, he gave me 5. But yet he heard all the numbers. So basically, we input all the numbers, he heard them, but he was not able, because the more I was going, the more he was forgetting the numbers. So this is exactly what happened to a recurrent neural network. So the more data it's being fed, the more it's going to forget some of the data, which creates what we call a vanishing gradient. Remember, we spoke about the vanishing gradient when we were speaking about the different activation function that can create a vanishing gradient. So now, because recurrent neural network is a network that depends on remembering what has happened in a certain sequence, or else it's going to give you the wrong model. There is a problem now of vanishing gradient, because of the fact that if the network is longer, the network may not remember all the data. So what's the solution? The solution will be the introduction of what we call an LSTM, which is called a long short memory. All right, so basically this is an example of an input in the recurrent neural network. So this input is the inputs at that state at the time t, right? So now the network needs to remember what has happened there. So that's the memory unit sequence at that time t, okay? So now this can be calculated by looking at the inputs that has happened previously, and the network is building up on that. But now, as we're moving through the network, we get to a point where the network can now forget. So that's where we're going to have a long, short-term memory network, where we introduce a different structure in a network. So LSTM is just a way of solving the memory problem in RNN. Okay, so you need to remember that when we talk about LSTM, this is just a type of recurrent neural network, right, structure, which is designed to just handle the vanishing gradient problem. Okay, so you must just remember that when we're trying to address the vanishing gradient problem in recurrent neural network, we're going to use an LSTM. Okay, so so basically in the LSTM, what we're going to have in the LSTM, we're going to have kind of a memory cell, right, that can store information for a long period of time. Okay, and then we have also what we call the gates. Okay, so the gates will just be used to control the flow of the information in and out of the memory cell. So these are the gates here, so which will be used for that. Okay, so we have an input gate which control new information, which is added to the memory, and then we have output gates which control the information that goes out of the memory. So basically, this is think about it like how can I say it? You know, for example, when you when you are given certain information, you go into a meeting or whatever meeting you go, or you are in class. What do? We know that our brain can remember, but we don't want to take a risk. So what do? We take a piece of paper, we write down certain information so that that piece of paper can be a reminder if we forget those information. So think of LSTM as a piece of paper that RNN is using to remember certain information. Okay. All right. So this is how we're going to solve the issue of gradient descent. Okay, so LSTM can be used in many scenarios. We have scenarios such as natural language processing. Remember, in natural language processing, when you're giving you're giving information, I'll give you an example. When you're using ChatGPT, it remembers what you've been asking before, and then as you're moving along with your questions and everything, it's continue learning, and then it gets to a point where sometimes it starts now giving you information that are not really, you can't really remember those type of information, especially when you're using a free version. It's going to limit you there. So those are issues that we can have, And then another scenario you have, for example, in speech recognition. If you say to you are using in your house is a smart house where you can tell the lights to turn off or turn on. So you can't just, the lights need to remember the whole sentence, everything that you are saying. It needs to remember when you say, please turn on the light. So it needs to remember there was a turn on, and then which was a command, and then what are you turning on? We're turning on the light. So it needs to remember all those things. Okay. So those are example of how LSTM can be used, right? But again, in recurrent neural network, we need to understand we have different type of recurrent neural network. You can have one-to-one, which means we have one input and one output, or it can have a one-to-many. That means it's a one input and then many output, and then many to one is many output, many inputs, one output, and then many to many, and then all right. And then we have a back propagation through time. Remember, guys, what we said last time? We said that most of the neural networks, such as the CNN, those are feed-forward neural network. What does it mean? It means information go from the input layer to the output layer. But now, remember now, in recurrent neural network, we need to remember what happened before. So there is a back propagation through time process that is happening inside the recurrent neural network. All right, because it needs to remember certain information and send back. All right, so this there is 3 steps in this back propagation through time. The first one will be computing the output value of each neuron through forward propagation, computing the error value in each neuron through back propagation, and then computing the gradient of each weight. Okay, so when we want to update the weights for everything, we use stochastic gradient descent. Remember, stochastic gradient descent is a type of gradient descent where we only updating for one sample at a time. All right, so so we spoke about LSTM. All right, so the third neural network after CNN and RNN, the third one will be the generative adversarial network, the GAN network, which is the most dangerous neural network being used these days, where you see all these fake videos, fake pictures that you see now on the internet. Some people are believing this is real, and then everybody keeps saying, oh, it's an AI video and everything. So those type of videos are generated using GAN algorithm. All right, so how does the GAN algorithm work? This is a neural network which works as 2 neural networks. So those 2 neural networks are playing 2 different roles. You have the first one, which is a generator, and the second one is a discriminator. So, and both neural network will be trained at the same time. So how is it going to happen? So the generator will actually generate fake images. It's going to generate fake data, right? That are really similar to the data that you have. So let's say, for example, you're dealing with, you have data, for example, of cat. So it's going to be generating fake images of cat. And the discriminator is going to determine if that image that was generated is real or fake. So that's how it works. So GAN can be applied in scenarios such as image generation, text generation, speech enhancement, and image super resolution. So when you see all these image generation, creating all these fake images, creating, you must understand it's the GAN neural network there, right? So basically, the generator will generate like fake videos, and then we take an input picture which is real, which will be taken into the discriminator, and then the discriminator will say if it's a real image or a false image. All right. So you must understand the output of the generator will represent an input in the discriminator. So the generator generates a fake image. We take that as an input together with the real data, and then the discriminator will determine what's the output, the probability. It's going to determine the probability that that can show us whether the sample is real. Okay, that's how GAN work. All right, guys. So and then we can have now problems that we can have in neural network. The problems that we can have in neural network, remember, we've mentioned this before, we can have a data imbalance. Remember, guys, what I told you last time, whenever you're training your model, make sure that your data, the type of data you are using, if you use 5,000 pictures, you want to determine between dogs and cats, please have at least 2,500 pictures of dogs, 2,500 pictures of cats. Because the data imbalance can make your classifier really biased. Okay, so you must understand that. So in image recognition, make sure all your data, you have enough data for each category. Make sure all your data are in the same sizes and all those things. That is very, very important, because it has been proven in many countries where they're trying to use an image recognition system where you find out that the image is good in identifying a certain race of people than another race. Why? Because when the system was being trained, they only used pictures of a certain race. And now the system is not smart enough. All right, so that is very important. So if you create a system to detect between male and female, make sure that you have enough pictures of male, enough pictures of female, so it can learn from both. Okay, so the data imbalance, so how do we solve that? We need to maybe do a random undersampling. So that means we're gonna delete certain samples. We can do an oversampling. It means we can add more samples, or we can merge it or do different things. So that's the first problem we have, a data imbalance. The second problem we have, which we've mentioned so many times, a vanishing gradient or exploding gradient problem. So what is a vanishing gradient? You need to remember, as the network layers increase, the more layers we have in a network, remember that we have a back propagation which send the error back. So as we're moving along, we realize that the value of the back propagation decreases, which causes a vanishing gradient. So the network loses memory. It loses information about the loss. You know, as we reducing the loss, and then it lose the information. So we have this vanishing gradient. Okay. So when we talk about exploding gradient, is as the network layers increase, if we have a problem where the backpropagation increases, which causes an exploding gradient problem. So how do we solve this problem? You know, that's where we have to look at what is causing the problem. Is that the data imbalance, or is it if in the case of the RNN, we can just include a LSTM, a long short memory. Okay. So that's how we're going to solve that issue. All right. So apart from the vanishing problem, we can also have an overfitting problem. So if your model become overfit, that is an example of you train a certain model, you did not use enough data, but when you're testing it, you think your model is performing well until you bring new data, and then your model cannot perform well because it was not trained with enough data. Okay, so in this case, you will see that your model will perform well in a training set, but very badly in a testing set. What can cause that? You have too many features dimension, or you have so many assumptions or parameters, too much noise, but you just have few training data. Okay, so as a result, what will happen is that the fitting function will perfectly predict the training set, while predicting result of the test or new data will be really poor. Okay, so the solution for that, you must maybe do a data augmentation, get more data. Or you can use what? Regularization. Remember regularizers? We have the L1 and L2 norms that we spoke about. And then you can do an early stopping or a dropout. Remember, these are what we call what was the name of this? When we use the L1 and L2 regularization, early stopping and dropout, how do we call this? Does anyone remember? What are this method? This.
Are they not normalizing methods?
Perfect. Those are normalizers. So what's the solution to overfitting? Using normalizers. You understand, guys? That's how simple it is. So to avoid an overfitting problem, use normalizers. Add data if you need to add data. Add a regularization. That means you can limit how your parameters are being set. So, for example, you can limit your weight in every connection. Your weight must be less than 5. So this can be a regularization. Okay, and then you have the early stopping, which means that you stop training at a certain numbers of epoch instead of finishing the whole sequence. And then you can use a dropout. That means you cut down a part of the neural network in training. All right. All right, so as a summary of this chapter has described the definition and development of neural network. We spoke about the perceptron, the training rules, common type of neural networks such as CNN, RNN, and GAN. And we also discussed the common problem of neural network in AI engineering and solution. So just before we close, can we just look at this quiz? True or false compared with the recurrent neural network? The convolutional neural network is more suitable for image recognition. True or false?
True.
Perfect. All right. True or false? GAN is a deep learning model, which is one of the most promising methods for unsupervised learning of complex distribution in recent years. As you can see, this is a complex question.
I would say true.
You will say true. Okay. Anybody else?
I would say false.
False. Yeah, it's true. Remember, we have a complex distribution. So basically, when we're trying to determine between pictures, like we want to generate fake or real pictures, and the reason why we say it's a type of unsupervised learning, it's because we just let the generator generate a fake picture, and then we get a new picture. So the whole point is just taking the real picture and the generated picture and putting them in the discriminator to get a probability whether this is a real or a fake image. So we kind of distributing them in that way, right? Single choice question. There are many types of deep learning neural network. Which of the following is not a deep learning neural network? Which of the following is not a deep learning neural network?
D.
Sorry?
D.
What did you say? You say A.
Logistic.
Logistic.
Yeah, logistic, D. This is not. This is it's a simple machine learning algorithm, logistic regression. So it's not part of deep deep learning neural network. Okay, so multi-choice. There are many important components in the convolutional neural network architecture. Which of the following are convolutional neural network component?
A, C, D.
You say A, C, D. Anybody else?
I said
B and
D.
D.
Guys, remember, this is a multi-choice. That means there's more than one answer. You have to be very careful with this. Which of the following?
BCD.
Sorry?
BCD.
B, C, D. Anybody else? Do we stick with B, C, D, or I heard someone saying A, C, D?
B and D. What about B and D?
B and D.
C, D.
So far, nobody has given a right answer. All right. Do we have a fully connected layer?
Yes.
Remember here, we're not talking about layers only. We're talking about convolutional neural network component. Anything that is part of. Do we have anything to do with pooling, a pooling layer?
Yes, we do.
We do. Do you have a convolutional kernel?
We have a conventional layer.
Yeah, but we also have a kernel, which we use in a convolutional layer. Do you remember when we spoke about the example of the first image that we have? And then we have a kernel, which we're going to apply to this layer to get a featured map. Do you remember this part?
Yes, sir.
Do you guys remember?
Yes.
Yeah, so we have we have a kernel, which is applied to the convolutional layer. So we have a convolutional kernel. Do we have activation functions?
No.
Yes, of course we have activation function. Remember, in the hand of the neural network, we need an activation function for between each layer. We need an activation function. We mentioned that. So we also have activation function. So in a CNN, we're going to have activation functions. We're going to have convolutional kernels. We're going to have a pooling layer, and we're going to have a fully connected layer. Type of activation function, for example, you're dealing with a multi-class. You can use things like softmax function. So you have all this, and in between all these layers, you can use a activation function like the ReLU. Can anybody tell me why I'm suggesting to use the ReLU as an activation function? Does anyone remember why we prefer to use the ReLU? Because the ReLU does not have a vanishing gradient problem. So that's why. Very important to use the ReLU. All right, guys, we can just turn on the camera and take our attendance, and then from next week, we're going to move into Python programming and actually create a small model where we're going to use convolutional neural network in practice. You see how you create a CNN. You will see how easy it is to create a CNN. Just a few lines of code. You create a CNN, and then we're going to test it, train it and test it and see how it's performing. All right, guys. In the meantime, any questions? By the way, I am currently uploading all the videos because I'm editing them as well. At the same time, I'm uploading and editing them through YouTube. It's taking me a lot of time, but I'm just going to, let me just cast the link here so that as I'm uploading videos, you guys can see it. Instead of me finishing all the videos, just 1 second, I'm going to do that. I'm going to post it here in the chat, and as well, I think I'm also gonna need to send it on the group. Or you know what? Let me, because here in the chat, once we close the, once we